So we'll do a quick example of linear regression in R. This is also the same kind of stuff you'll be doing for your project, the very last part of that project assignment. And I'm using data that I actually got from one of the Against All Odds videos. They have these student guides that I've been posting. If you happen to take a look at them, they have a lot of questions. I've gotten some of your homework questions from that. And so I just extracted some data from one of those exercises related to fish length. So they went and caught a bunch of fish, measured the length in millimeters, and then they sampled the tissue of the fish for mercury concentrations. So the thought is, well, people eat fish, they get mercury because mercury bioaccumulates. Mercury is kind of in the water and in the sediment. Fish eat bugs that eat the plants in the sediment, and then little fish get mercury in their bodies, and then bigger fish come along and eat them, and then the bigger fish get more mercury in their bodies, and so the concentration of mercury accumulates and increases the bigger the fish is, because it's called this like trophic cascade. So that's the theory, and the idea here is, well, let's take a bunch of measurements of different fish and figure out what the relationship is between mercury concentration and fish length. And then from there, can we say, okay, it's safe if we think the average person is going to catch 4 fish, what is the kind of threshold that we should say, don't eat this fish because it's going to have too much mercury, and mercury is bad for our brains and causes birth defects. It's terrible. Okay. So we got this data. I'm calling it fish data. So fish HG from mercury.csv, and I'll post this on Canvas. I'll use the head function to show me just what this data looks like. So it has 2 columns, length and concentration. So length is in millimeters, concentration is in nanograms or micrograms per gram. So micrograms of mercury per gram of tissue. Okay, let's plot the data. So here's a nice scatter plot. We can see looks like a positive linear relationship. Okay. Length on the bottom in millimeters, concentration on the y-axis. So concentration is our response variable, length is our explanatory or dependent variable. Okay, the next step is we're going to fit a linear regression model. It's pretty straightforward. LM is the function that we're going to use, and that LM just stands for linear model. There's a number of ways to do this. The most basic way, I think, is this kind of syntax. And so our data set is called data. Within data, we have 2 variables or 2 columns, length and then concentration. So the way this is phrased is concentration, which is just the name of that column. As you can see over here in my environment over here, data, I say concentration tilde or squiggly line length. And all this means is that concentration is a function of length. So this is basically an equation that we're putting in there, or a function. And we just tell it to look for those variables in data, in our data set. So this is a linear regression model. I'm putting it into this variable or this object called fit. So fit is going to store our linear model. And then we can do summary fit. And we get a lot of information. So what it does is when I do summary fit, it gives me my equation again. It shows me my residuals. So the minimum, maximum, median, just some sample statistics of my residuals. Then it tells me my coefficients. So the estimate of my coefficient for the intercept is negative 0.7. So that means the y-intercept is negative 0.7. And then length is my slope coefficient. So it gives me the slope coefficient for length. If I had more variables, then it would give me the slope coefficients for those other variables. I also have some more information here. This is the standard error of this intercept, so the uncertainty associated with it. And you can actually run a t-test on it and see if is it significantly different from 0. So this ends up being a 2-way t-test, a 1-sample 2-way t-test. Are we different from 0 or not? And this probability value tells you if you are or not. So in this case, it says the intercept is in fact significantly different from 0, and then the length is in fact significantly different from 0. Okay, great. We get an r² value. We'll talk about r², right here. We'll talk about r² next time. That's our last lecture. And then finally, it gives you an F statistic. I go into this in more detail for the project, but basically what this testing is your model, the linear regression model, a significant model? Is it a real model versus just a mean value, like a flat line, basically? So this is a test on the overall model, and it tells us that we have a significant model. Okay, great. So that's just kind of the diagnostics. A couple more things we can do. We can extract the residuals. So if you use the function residuals on your model, so the model is stored in fit, or residuals is a function, it just extracts those residual values. So I store those in R, so R for residuals. I can do a QQ plot using the QQ norm function, and then add a line to it. And I can look at my overall, the distribution of my residuals. And you know what, they're pretty close to the line for the normal distribution. So that looks like we have a pretty good fit. I can also plot my residuals. So I just do plot R, and I can look at how even the variability is distributed. I don't see any signatures here. I don't see any patterns other than just kind of randomness. And it looks like the width is pretty equal. So that looks good too. Now I can extract the coefficients using this coefficient function. It just takes those intercept and slope values out and stores it into this object coefficients. So you can see it has the intercept value and the length value for the slope. Now I'll plot my data again. And then I can use this function AB line. So A is the intercept, B is the slope. AB line, I give it A and B, the intercept and the slope for my coefficients. And so what that does is it fits a line to the data and plots that linear regression line. So that's how I would plot it kind of most quickly. Note that it's going to extrapolate out beyond the data. So we want to make sure we don't interpret that as being reasonable, but that's just how you would plot it very quickly. What I'll do when I record that extra little bit about confidence intervals and prediction intervals, I'll show you how to calculate that in R as well. There's a couple more steps to do that in order to either calculate the actual confidence interval or prediction interval and then plot that as these bands across the regression plot.